Imagine a tangled web of wires, resistors, and power sources. How do you make sense of the currents flowing and voltages dropping? How do you predict circuit behavior without trial and error? The answer lies in two fundamental principles that form the bedrock of circuit analysis: Kirchhoff's laws. These aren't just abstract theories. They are practical tools that empower you to dissect and understand any electrical network. Every electrical circuit, no matter how complex, adheres to basic conservation principles. These laws, formulated by Gustav Kirchhoff in the mid-19th century, provide a systematic way to apply these principles to circuit elements. They are indispensable for anyone working with electricity. We'll break down each law, understand its underlying physics, and see how it applies to real-world circuits. Get ready to demystify even the most daunting circuit diagrams. First, let's tackle Kirchhoff's Current Law, often abbreviated as KCL. This law is a direct consequence of the principle of conservation of electric charge. Simply put, charge cannot be created or destroyed within a circuit. KCL states that the algebraic sum of currents entering any node or junction in a circuit is equal to the algebraic sum of currents leaving that node. Alternatively, the total current entering a node must equal the total current leaving it. Think of it like water flowing through pipes. If you have a junction where several pipes meet, the total amount of water flowing into that junction must equal the total amount flowing out. Water doesn't accumulate or disappear at the junction. In electrical terms, a node is a point where two or more circuit elements connect. All points along a single wire with no components between them are considered part of the same node. When applying KCL, we typically assign a sign convention. Currents entering a node are often considered positive, and currents leaving are negative. The sum of all currents at that node then equals 0. For example, if 5 amps flow into a node and 2 amps flow out through one branch, then 3 amps must flow out through the remaining branches. This law is crucial for analyzing parallel circuits and current dividers. Next, we move to Kirchhoff's Voltage Law, or KVL. This law is based on the principle of conservation of energy. It states that the algebraic sum of all voltages around any closed loop in a circuit must be equal to 0. Imagine walking around a roller coaster track. If you start at a certain height and complete one full loop, you must return to your starting height. The sum of all elevation changes, both climbs and drops, must cancel out to 0. In a circuit, a closed loop is any path that starts and ends at the same point, passing through various components. As you traverse this loop, you encounter voltage rises across power sources and voltage drops across resistors or other loads. KVL dictates that the total energy gained by charges moving through voltage sources must be exactly equal to the total energy lost by charges as they pass through resistive elements. Energy is neither gained nor lost in the loop. When applying KVL, we choose a direction to traverse the loop, either clockwise or counterclockwise. Voltage rises, like moving from the negative to the positive terminal of a battery, are typically taken as positive. Voltage drops, like moving across a resistor in the direction of current flow, are taken as negative. This law is fundamental for analyzing series circuits and voltage dividers. It helps us understand how voltage is distributed across different components within a closed path. Kirchhoff's laws are rarely used in isolation. They are powerful when combined to solve complex circuits with multiple loops and nodes. The key is to apply them systematically. Here's a general strategy for circuit analysis using KCL and KVL. First, identify all the nodes in your circuit. Then, identify all the independent loops. An independent loop is one that contains at least one branch not included in any other independent loop. Next, assign current directions for each branch. If you guess wrong, the calculated current will simply be negative, indicating the opposite direction. Also, assign voltage polarities across resistors based on your assumed current directions. Current flows from higher potential to lower potential. Now, write KCL equations for each independent node. Remember, you only need N1 KCL equations for N nodes, as the last one will be redundant. Then, write KVL equations for each independent loop. You will end up with a system of linear equations. The number of equations should match the number of unknown currents or voltages you need to find. Solve this system using algebraic methods, matrix operations, or even software tools. This systematic approach transforms a seemingly chaotic circuit into a solvable mathematical problem. It allows you to determine every current and voltage within the network. While powerful, applying Kirchhoff's laws can have its challenges. One common pitfall is inconsistent sign conventions. Always stick to your chosen convention for voltage rises and drops, and for currents entering or leaving a node. Another challenge is correctly identifying independent loops and nodes. Practice with various circuit configurations to develop this skill. Drawing clear circuit diagrams and labeling all components, currents, and polarities is incredibly helpful. Remember that KCL applies to current at a node, while KVL applies to voltage around a closed loop. Don't mix them up. Also, ensure you have enough independent equations to solve for all your unknowns. These laws are the bedrock for more advanced circuit analysis techniques like nodal analysis and mesh analysis. Mastering KCL and KVL is the essential first step to understanding virtually any electrical system. Kirchhoff's Current Law and Kirchhoff's Voltage Law are more than just equations. They are fundamental principles that govern the behavior of all electrical circuits. They embody the conservation of charge and energy, respectively. By understanding and applying these laws, you gain the ability to analyze, design, and troubleshoot complex electrical networks. They are indispensable tools for students, engineers, and hobbyists alike. So, take these principles, practice applying them to various circuits, and watch as the mysteries of current flow and voltage distribution unravel before your eyes. Your journey into advanced circuit analysis starts here.